Okay, so last class was online class, and you learned about intervals, or more exactly, you learned about the indefinite interval, which is also called the antiderivative. So that's the antiderivative in the indefinite interval, which is the same thing. So if I gave you a function, how would I find the antiderivative of this function? What rule did we learn? How do we figure this out? What would be our antiderivative, our interval of this?
N plus would be like x to the n plus 1 over.
So we learned what's called the power rule of integration. I have x to the n dx. When I integrate that, it becomes x to the n plus 1 divided by n plus 1. So we're undoing their derivative. Okay? To find the derivative, we move the power to the front. And so we're multiplying. Instead of multiplying by that power, we're going to divide. So undoing that. And then we subtract 1 to the power. So undoing subtracting 1 to the power, we add 1 to the power. So we're just doing the opposite operations. So what would that look like in this example here? What would be my interval?
1 plus x squared, or x cubed plus 2x squared minus 5x plus c.
Plus, what's your next one?
Plus 2x squared minus 5x plus c.
Okay, so a couple questions here. How did 3x squared become x cubed? What did he do in the background there? How did he get that? All right, so let's think about it step by step. Yeah, so let's look at he's practiced before, so maybe he can see it in his head. So we're going to do the rule here each one. So we're going to do each of these individual. So add 1 to my power here, that gives me x to the 4th, and I divide that by 4. Now this one has a constant, so I just bring that constant out, and then I'm going to do the same thing with the x squared. So I'm going to take my x, increase my power by 1, and divide by that power. And notice here we got 3 divided by 3, which gives us the 1. So he did that simplifying there. So that's what that happened. And so here I'm going to bring that constant out, and I'm going to use my power rule with x to the 1 power. So that becomes x squared over 2. And then 4 over 2 simplifies to that 2x squared. And then this negative 5 is understood to be x to the 0 power. We just don't ever write that because 0 power is x to the 0 is 1. So I have x to the 0. If I increase that, that becomes x to the 1st power over 1, which just simplifies down to the 5x, the negative 5x. Why do we have to include this plus c? Huh? It just represents that there can be some constant. We don't have enough information to figure out what that constant is at this point. We will in some problems be able to figure that out later on. But now we can't figure out what that constant is, so we just call it a c, some random constant, because I know when I take the derivative of a constant, it just comes 0, so I don't see it up here. It disappears. And so I could simplify this. You can either write it as x to the 4th over 4 plus x cubed plus 2x squared minus 5x plus c. Or you can bring that over 4 and write it as 1/4. It's your personal preference which way you write it. I'll try to change it up on how I do the multiple choice or the options that you have on that. So that's what you learned the last class. Any questions or any of those homework problems you had difficulty with that you want me to go over, that you weren't confident about, or just wanted clarification? We're good? Okay, so that's antiderivatives or indefinite intervals. They are the same thing. All right, last night's video was over Riemann sums. So you learned about Riemann sums. Now the reason why we started talking about Riemann sums is this allows us to estimate the area under the curve, in between the curve and the x-axis. And that is our second main question of calculus. What was our first question? What was the first thing that we talked about mostly all so far this year?
How to find the slope at any point.
How to find the slope of the tangent line at any point. Okay, so the slope of the tangent line was our first main question. That was derivative. Derivatives were answering that question. How do you find the slope of the tangent line? So that was the big question. So now our next big question we're going to spend the rest of the year talking about, or rest of our semester talking about, is how to find the area under a curve. And that's integrals. Helps us find the area of the curve. Definite integrals to be exact. So that's going to help us find the areas. So before I can figure out the exact, we're going to start introducing it by doing our estimates. And Riemann came up with this. And we have our Riemann sums to estimate this. There are 3 Riemann sums. We have our left-Riemann sum, abbreviated with an L. And this subinterval tells you how many rectangles you want to form. So I see L3, that means I need a left-Riemann sum with 3 rectangles. R3 tells me I want a right-Riemann sum with 3 rectangles. And M3 tells me I want a midpoint-Riemann sum with 3 rectangles. Now, the T3 stands for the trapezoidal rule. It's not technically a Riemann sum, it's actually discovered later on after Riemann, but it uses some of the same properties. Instead of forming rectangles, because Riemann just focused on forming rectangles, you form a trapezoid. And we put it in with the Riemann sums because the process is very similar, but technically it's not a Riemann sum, but it's called the trapezoidal method or trapezoidal rule that you can talk about on that. All right, so if I saw this notation, fine, what is that telling me to do?
The left sum of
5 rectangles. I need to subdivide my domain, whatever x values domain I'm looking at, into 5 equally intervals, subintervals, and that's what we're going to have to do. So that's using the left-Riemann sum. Okay, first thing I'm going to do is just learning about graphing it and seeing what this looks like. So what I want you to do is copy this graph 4 times, 1 for each of the Riemann sums that we're going to do. So I'll give you a moment to do that. Copy that graph on your paper, repeat it 4 times, and then we'll work with it. Yeah, graph paper would come in really handy right now. Makes it easier. You can see the equation is y equals 1/2 x plus 5 that I sketched here. And you don't have to go all the way if you don't want to. Notice that I'm going to go from 0 to 6. Because my subinterval here is 0 to 6. So just make sure you have it graph from 0 to 6. Yeah. Yes. Well, no, and then if you move on to the next test, keep it on the same sheet. Okay. We're going to put all the matrices on that sheet. Yep. You're just giving me electronic testing. No question. Okay, then I got the graphs done. All right, so let's look at, I want to figure out this A1 here. We're going to do left-Riemann sum of 3 subintervals. So first thing you got to look at is look at your domain. I'm going from 0 to 6. I need to figure out, since it said that these are going to be equal width, subintervals of equal length, I need to find delta x. So that's going to be my first thing to figure out, and that's the width of each of the rectangles. Delta x is the notation used for the width of each rectangle. So we want to do delta x. And to find delta x, if they're equal subintervals, what you do is you take the ending of your interval minus the beginning of your interval. We usually use A and B. So we take the end of my interval minus the beginning of my interval divided by n. Now this only works if they're equally widths, equal length intervals. And so in this case, my delta x will be 6 minus 0. Oh, I forgot to record. No, I am recording. Good. Okay, 6 minus 0 divided by n, which is 3. So what is my delta x represent? What does that equal to here? 2. So that tells me I go to my beginning of my interval, which is 0, and I go 2 for each time on my x-axis. So I go 2, and that's going to be, there's my first rectangle. It's going to have that width from 0 to 2. My next rectangle goes 0 to 4, and then 0 to 6. You can see I'm going to get 3 rectangles. Matches up with that 3 there. That's the first thing you check. Next, you look at your symbol. We want to find left-Riemann sum. So the left endpoint of each interval, each rectangle, decides the height of the rectangle. So if I want left-Riemann sum, this first rectangle I would draw to the height. So I hit the line on the left of that endpoint, and then I make a rectangle. So that's my first rectangle for this Riemann sum. My next one at height at 2, find where that hits my axis, and I go down. Last one, the height at x equals 4, and out. And so that's going to be my rectangle. So this is the area I'm actually finding. Oops. Too far down. And it doesn't let me delete that. For some reason it doesn't like to delete all of this. Well. Okay, so that's the area that I found. Okay, this would be left-Riemann sum would give us this estimate, this area. So that's what our sketch looks like. If I ask you to do the sketch, that's all you have to do. That would be the sketch of this. Now, if I wanted to figure out the actual value of this, let's think about this. To find our left-Riemann sum, let's up a little bit more room. Let's talk about how to find the area of a rectangle. Length times width. So my length here is my delta x, and my width here is my length. My width here is my function value at 5. Well, at 0. Sorry, function value at 0, which is 5. Okay. Now, what would be the area for the next rectangle? I still have my delta x times, but now how am I determining my height? F at 2. And my last rectangle is my delta x times f at 4. Now, what do we notice if I plug in my delta x, which is 2? What do we notice about this? Is there an easier way I could have wrote this?
I think.
So I could have taken out my delta x. I could factor out my delta x and just write this as delta x times the function value at 0 plus the function value at 2 plus the function value at 4, which is going to be, let's see, function value at 0 is what? 5 plus what's the function value at 2? What was that? 4. Okay, so we got 5 plus 4 plus 3. All right, 5 plus 4 plus 3 is times by 2. So I would estimate my area is 24. Now, is this an underestimation or an overestimation?
Over.
Over. Okay, how do you know it's over?
You look at the line.
You can look at the line and see that I got some shaded area above each of those lines. Or what if I didn't sketch the graph? How could I figure it out?
Because it's the left. Because the left sum we're not doing interval. It's so function is decreasing.
So if the function is decreasing over that interval and you're doing the left-Riemann sum, it's always going to be an overestimate. Okay? Now, here I just want you to sketch the graph of R3. And I want you to find it to sketch it. So sketch the graph of the right-Riemann sum, the 3 subintervals. Still doing from 0 to 6. So the same interval for all of these. What do you think? Is this going to be over or under? Very good. It's going to be an underestimate. Okay, so my delta x stays the same. It's still 2. I'm going to partition my x-axis out. 2, 4, 6. But this time, I'm going to use the right endpoint of each rectangle. So it's going to start at f of 2 and get my height. Then my f of 4, get my height. And then my f at 6 and get my height. And so this is the area that you're actually finding. So that would be what's represented. And yes, this is definitely an underestimate. Okay. Now do midpoint of 3 rectangles. How do you think we're going to do this one?
Move off the right. No.
So you still, my delta x is the same. So my interval is from 0 to 6. So my delta x is still 2. So each rectangle is going to be 2 widths. So there's my rectangle. But to determine how high it is, I look at the midpoint of that interval. So I have to figure out what's the number in the middle of this interval from 0 to 2. 1. So I look at f of 1, and that determines the height of the rectangle. So my first rectangle would be at a height of f of 1. What would the height of my second rectangle be? At f of 3. And then my third rectangle, height at f of what? F of what? For the last one? 5. Well, the midpoint between 4 and 6, which is f of 5. So we're going up at actually 2.5.
Wait. Okay, so the midpoint is,
The midpoint of each rectangle.
uh,
That's what that midpoint stands for. You find the midpoint of each rectangle. Is this an overestimation, underestimation, or exact?
it's not exact, but it's both an over and.
How can it be both over and under?
I mean, which says a.
Yeah, my drawing doesn't look very good, but it would end up being an exact. Because every over is going to be the same under, and that's only because our function is linear, which is a straight line with a constant slope there. So in this case, it will be. Normally, that doesn't work, and we'll talk about that later today, but just in this case, it is. So that's going to be our graph for it, because technically, all of, this is the one that looks the best, the closest. This area and that area, that rectangle actually should be the same if you're truly at the midpoint. Okay. Now, our last one, trapezoid method with 3. So I'm still looking from 0 to 6. And so if I do my b minus a over 2, I still get the same delta x. It's still 2. So I'm going to go from 0 to 2, 2 to 4, 4 to 6. That's my proportions here. Now, how do I draw the trapezoid? That was from the video. How do you draw this one? Because think about it, usually you you see a trapezoid that looks like this, kind of like that. Well, we're just turning that on the side. So we're drawing something that looks like this. That's the trapezoid. We're going to be making these trapezoid methods. So it's always going to look something like that. So what you do is you use the height at the beginning of the interval for this beginning height. Use the height at the end of the interval for your ending height, and then you draw a straight line connecting that beginning to the end. So that would be your trapezoid that you make. So for my second one, I need the height at f of 2, x of 2, and then ending at x of 4, f of 4, and then connecting. And for my last one, f of 4 to f of 6, connect with a straight line. And so that would be our area that we're finding. So I'm just making trapezoids here. And that would be our estimate. Okay, what kind of estimate would this be in this case? That'd be exact. Again, just because it's a linear equation that we're working with. But that would be our trapezoid method. Okay. Now go to Canvas and work the first 6 problems. I'm not going to require you to the graph. I give you a matching on these. So you don't have to draw the matching. You don't have to draw the graphs with you. So there's very little work on these first 6. Now you might have to draw the last 3 problems, problems 4, 5, and 6, if you to try to figure out which order it is. That's okay. You need to work on that. You can figure out without the work. That's okay. There's not a lot of work from the first 6 problems. Pause recording. Okay. So we've already figured out that, oh, I still have it frozen. Okay, so we already figured out that if our function value is increasing, okay, so our function value is increasing like this, is our left going to be an overestimation or an underestimation? Underestimation. So let's say I have it like this, my left endpoints would look like this. So that's going to be an underestimation. So L of n is an underestimate. And R sub n is a, okay, that would be an overestimation. Okay, if I drew that on here, I would have to go up to this height. So I'm going over each time. All right, now if f of x is decreasing, then L of n, the left-hand side is what? So now I'm thinking of this graph. Yeah, because we're looking at, well, now we are decreasing. So if I'm doing L, it's going to look something like this. So that does over. So L of n is overestimation. What's R sub n? Okay, and this would be an underestimation. Okay, underestimate. Now, notice I'm just saying increasing, decreasing only tells us left and right. I haven't talked anything about midpoint or the trapezoid. In order to talk about the midpoint and trapezoid, you have to look at the concavity. If f of x is, let's see which one I want to do first. Concave up. Okay. So if f of x is concave up, see if we can figure out the rule for this one. So concave up means we have a smelly face. So let's say I have something that's going like this. That's concave up. Or we could have concave up like this. Either one of the sides of the smelly face, right? Okay. So if I wanted to figure out, let's try our trapezoid method. Trapezoid method. So if I'm doing the trapezoid method, I go the height here, and then connect with a straight line. The height here, connect with a straight line. Okay. And then my height here, connect with a straight line. Okay, what do you think that is? It's slightly over. Even if I do it over here, maybe if I make these intervals a little bit bigger, you can see it a little better. And those are my intervals for the trapezoid method. So if it's concave up, the trapezoid method is an overestimate. Okay. Now, if I'm looking at our midpoint interval, so if I do my midpoint here, I go like this. And it slightly becomes an underestimate. So we have a little bit better, we have a little bit bigger rectangle. I think you can see it best here. You can see that's a more space that's not included than the one that's missing there. So we have an under representation. So that's going to be an underestimate. So concave up, the trapezoid method is an overestimation. The midpoint method is an under. And then the last one is f of x is concave down. Spell that correctly. It will be the opposite. The trapezoid method is an underestimate, and the midpoint method is an overestimate. That might help you get some of those in order to look at. So get that in your notes. Make sure you know those. You can know those four things there. And memorize them. And that's crucial information for Riemann sums and how they relate to each other. All right, now you will often see Riemann sums used in application problems. I'm going to do a couple of basic examples. And in real life, I mean, think about it. When you're doing an experiment or you're collecting data from a survey or something like that, you're not going to know the function value. So a lot of times in these real life applications, we're just going to say the f of x. We don't know what our function is. Sometimes you can find it out or estimate it using regression. But a lot of times in real life, you're not going to know the function value, so you got to use a table. So that's what we're going to talk about now, is how to figure out the left-Riemann sum, the right-Riemann sum, the midpoint, and the trapezoidal method using a table of values. Now you'll see two types of tables. One like this one, which was nice and convenient, and the person thought ahead and did nice intervals, equally spaced intervals, where they found the data. So this is where we will have a delta x. If the spacing is nice and equal, then you can find a delta x. And we'll be able to use it just like all the other problems that we've done so far. But a lot of times, for some reason, either for convenience sake or just because they didn't think ahead, your data might not be collected in nice even intervals. In that case, we cannot use a delta x. We have to do each rectangle or each trapezoid having an individual different width. And so we have to make a little adjustment. So that's the first thing you want to look at. You want to look at your table and see if the x values are equally spaced or not. If the x values are equally spaced, your next step is to find delta x. Now let's read what we want to look at. We want to use the table of values to estimate the interval from 0 to 6 of f of x dx. And I'm going to do 3 equal subintervals. So first thing, if I'm going the interval from 0 to 6, that tells me the beginning of my domain is 0, the end of my domain is 6. So A is 0, B is 6. And I'm doing 3 equal subintervals. So my delta x is going to be the same as the last problem, 6 minus 0 over 3, which gives us a 2. So our delta x is 2. Okay, so that's the first thing you want to identify. Then this is what I like to do. I like to go to my table, and I'm going to make those 3 rectangles. And I'm going to say, okay, I need a width of 2. So if I start at 0, and I start at my beginning of my interval, start at 0, my first rectangle will end at 2. So I have one rectangle going from 0 to 2. And I'm not actually going to draw these rectangles this time, I'm just going to visualize what's happening. Then my second rectangle has to start at 2 and end at 4 of x and 4. And my third rectangle starts at 4, ends at 6. So you can kind of see your rectangles there and looking at your data that you want. Now, we'll do A. A asks us to find a left-Riemann sum of 3 equal subintervals, so that's L3. So I'm going to do, just like we did before, I could do the shortcut. I'm going to take my delta x and factor it out. And then I'm going to times it by, from left, this red rectangle, which one should you start with? The function value at 0, the function value at 2. Function value at 0 because I'm looking at the left side of that rectangle. So this is going to be my f of 0. For my green rectangle, what should I start with? My function value at x of 2, so f of 2. And for the blue rectangle, we're looking at f of 4. So you can skip this step here. This is just showing you the setup. What I'd like to see on your first thing to write, well, first thing is this, of course. I mean, you found your delta x, that's the first word. You're gonna have to show work on these. So find delta x is your first word. Second word is actually just plugging it in. So delta x is 2, f of 0. What is f of 0 equal to? -6. Just look at the table. Just plugging in the table. So that's -6. Plus what's f of 2? 8. Plus what's f of 4? 30. This is the second piece of work I want to see on your paper. Okay, substituting into that new formula that we have. Then you can go straight to your calculator, or I can do this in my head. And we're going to figure out what this is equal to. So -6 plus 8 gives us what? 2 plus 30 times by 2. So our estimate is 64. That's it. That's our Left-Riemann Sum estimate for this.
So it's the delta x equals 0 divided by
Divided, so the formula for delta x is b minus a divided by n. How many subintervals you want?
oh,
So that's what that comes up. That's the formula for delta x. When they are equal subintervals. Okay. So how would I find my right-Riemann sum for this problem? We'll skip straight to the work. Is the delta x the same or different? Same, so I don't have to show that work. You go straight to my delta x. Okay, what is my first value I'm going to plug in? We're fine. F of 2, what is f of 2? 8. So you can skip that middle step and just go straight to this. So that, my first value, now I want the right, so look at this red rectangle and finding the right endpoint. Well, that points to 8. Okay, plus what's the right endpoint for the green rectangle? It'll be 30 plus 80. Okay, equals, and then you go straight to your answer. So this is showing the minimum work you have to show. Again, we see you had at least delta x for the first time. So what do we get there? Okay with 92?
Yeah.
Okay, so that's our right. Questions over how I found the right. All right. Yep. Oh, it should be 80. I'm really off. Sorry. Thank you.
Wait.
The number is 8.
Oh.
I wrote 8 for some
I was
reason.
like, was our?
No, I wrote the wrong number down. It should be 80.
110.
Thank you for finding that.
183.
Yeah, because I knew it should have been something larger. What did you get?
Yeah.
236. All right. Okay.
Feel like I'm doing that thing.
Now I gotta watch myself. All right. Now we're gonna do midpoint 3. Okay. So what's the width of each rectangle? Is it changed or is it the same? It's the same. Okay, but this time we want the midpoint of the red rectangle. What's the height of the midpoint of the red rectangle? F of 1, which is 0. Plus
18.
18
Plus 60.
plus 50.
68 times 2, 136.
Okay with that? Okay. Now I'm gonna give myself some room. So let me clear off some space. So I'm gonna show more work for the trapezoid. This is the first time I was doing the trapezoid. Right-Riemann Sum was equal to 236. And our Midpoint-Riemann Sum was equal to 136. Just want to make sure I remember those numbers. All So let's talk about trapezoid now. So from the video, how do you find the area of a trapezoid?
Is it's the base. So it's base times the average.
Okay, all right, so I have my average of the two heights. Now remember, our rectangle that we're going to draw here, we have our base times average of two heights. All right, so if you think about it, if I'm doing this red rectangle, I have starting here at 0, ending at 2. I have a height at -6. Then I have a height at 8. Okay. So I'm going to make my trapezoid is going to, we're going to connect those two endpoints and then I go to our x-axis. This looks a little bit different though. Let's not do it with the negative the first time to show it. And then we're going to do something like this. So that's going to be our general trapezoid. It's going to look something like that shape. Okay. So our base is represented by delta x. Our width is our thing. The height of this first one is represented by my first x value at the beginning of the interval. This height here is represented by my y value at the end of the interval. And how do you average those? How do you find an average between two values? Divided by that amount. So if I wanted to do this trapezoid method and do the red trapezoid here, I would take my delta x, which is 2, and then I times this by my function value at 0 plus my function value at 2 and divide that by 2. Okay. Looking at my next trapezoid, the green one, I take my delta x, which is 2, times that by my f at 2 plus my f at 4 and divide that by 2. And then my blue one, I take my delta x, take my f at 4 plus my f at 6 and divide by 2. Now, that took up a lot of space. Is there a condensed way I can write this?
You equal to this question about is there any question?
So I could say, okay, I take my delta x divided by 2. In this case, I get 2 divided by 2, which is 1, so I just canceled out, right? Now, I'm going to times that by, because I can take all of these. I can take the multiply by 2 and dividing by 2 out from each of these fractions. Okay, what does that leave us with? Well, that leaves us with f of 0 plus, well, there's an f of 2 and another f of 2. So that's 2 f of 2. Plus, well, there's an f of 4 and another f of 4. I can combine that with 2 f of 4 plus f of 6. So what I noticed is in the trapezoid method, you can decrease it by, take your delta x, divide it by 2, your first endpoint of your first rectangle, only written once, plus all intermediate. Notice how each of these are drawn twice. All those intermediate ones, you have to take its height twice. So 2 times the height of 8 plus 2 times the height of 30. Plus, and then this endpoint, notice I only drawn it once, so it only occurs once. So I just do 8. So the beginning and the ending of once, all the ones in the middle are get doubled. If you remember that formula, you can save, you don't have to do all this work, you can skip straight to this. Because for the red one, I have to take this height and this height, add that together and average it. The average I brought out. So I add that together. But for the green, I got to take this height again, and then this height. So each of the ones in the middle get doubled. And so that's, this right here is the first one that you have to see after you find your delta x. And then you can just plug that in and get your answer. So what is our trapezoidal value equal to? I don't remember this one.
150.
That sounds right. Yeah, 150. So our answer here is 150. Now, we don't know the shape of this graph. But what do you think would be our best estimate of these? Because there's a range of answers from 64 all the way up to 236. What would you think would be our best estimate of this data? The trapezoidal. And if you're doing that trapezoidal, is usually the closest because you're making that trapezoid instead of a rectangle. So you always end up making a little bit slightly better estimate. Okay. Now, here is what you're actually going to see. It's usually like a word problem situation. And so this is the data. The table shows the rate in liters per minute at which water leaks out of a container. So T is time in minutes. R is our liters per minute in our container that we have. We want to do a right-hand Riemann sum to compute using 4 subintervals indicated by the data in the table. Okay. First thing I look at our data in the table. Are our data collected at nice equally spaced intervals? No. Okay. So that meant we will have no delta x in this problem. Each trapezoid will have its own width, slightly different than the other. So we will not be able to do the shortcut with this one. Now, I want 4 subintervals. So I look at my data and see how can I use the information I have to make 4 groupings. Well, I could do 1 here, 1 here, 1 here, and 1 here. So that lends it nice and neat to 4 subintervals. Okay, you would have to look at your data and see which one it lends it to how you break it out. But again, I do like drawing that on my table, so it helps me figure out what I'm working with. So now I want to do a right-hand Riemann sum. So right-Riemann sum of 4 intervals. But this time I got to find the area of each individual rectangle because they're not exactly the same. How do I find areas of rectangles? Length times width. So to get my length, I need to figure out the distance in my x value. So how far is it from 0 to 1.2? So that width is a 1.2 times by what's our height? For a right Riemann sum. So which height should I be looking at? Huh? The 4.3, because that's at the right end of that rectangle. So I'm going to times that by 4.3. Plus, we move to the green rectangle. What's the width of this green rectangle? 1.1. So it's different. That's the reason why I couldn't use a delta x. Because they didn't collect the data in nice equal space. Now times that by our height at the right endpoint, which would be 3.1. That gives us that area. Okay, now I'm going to do the blue one. What is its width? 1.5 times it by its height at the right endpoint. which is what? What's that height? 2.2.
Okay, I would-
And then the purple rectangle, what's its width?
2.6.
Okay, everybody know how we're finding that 2.6? What are they doing to get that? You're taking 5.4 minus 3.8. So let's figure out what that is. That's 1.6. That's the 6 you gotta borrow to get this. So that then becomes,
Oh, I did.
that becomes the one there. So that's 1.6.
Okay.
And what's the height?
1.5.
1.5. Okay, so that's the work I want to see on this type of problem. That shows me that you know that the delta x is not the same. Then you just punch in your calculator and get an answer. I think I got 14.27. That would be my estimate rounding to 2 decimal places. Any questions over that? All right, work the next grouping, 7 through 11. Yes. All right, let me push pause. Okay, we're not going to do all of these, we're only going to do certain parts of it for time. So this time, if the interval from 0 to 2 of 2x squared plus 3 delta x is approximating using a right-Riemann sum, a left-Riemann sum, a midpoint-Riemann sum, or a trapezoidal rule with 4 equal subintervals. So that's the first thing I want to recognize is I'm doing 4 equal subintervals here. Then the approximation is blank. Is this an over or under estimate? Okay. So I notice this information here. So what is the beginning of my interval? What is the ending of my interval that I'm looking at? 0 to 2. I want an equal 4 equal subintervals. So let's find delta x. So how would I figure out delta x? 2 minus 0 divided by 4. We have 4 equal subintervals. So I'm counting by 1/2 on my x-axis. So to kind of help me kind of figure out what this is, I'm going to go 1/2, 1, 3/2, 2, and that's going to give me my intervals. 0, so 0 to 1/2 is 1 rectangle, 1/2 to 1 is the second, 1 to 3/2 is the third, 3/2 to 2 is my fourth one. So it gives me my 4 subintervals. So I'm just putting that there. Now you draw on the graph, just give me an idea what to work with. Now we're going to do A. We're going to find our right-Riemann sum. So since I have a delta x, I can bring it out to the top. And then what am I going to multiply by? My function value at what x? So right-Riemann sum. Not 2. This is my division. These are my 4 rectangles. So where's the right endpoint of my first rectangle? At 1/2. So I need my function value at 1/2. That's going to be the height here. I need to go up to 1/2, wherever that is. I don't know where it is now, but I need to go up to 1/2. And then what's the next height for the next rectangle? At f of 1. And then f of 3/2 plus f of 2. With that, 1, 2, 3, 4. We have 4 numbers for my 4 rectangles. Okay. Now, to help us out, instead of doing all of these plugged in individually, I need to find these individual values. If you show this is good work. Now my function value is x, 2x squared plus 3. And I need to find f of 1/2, f of 1, f of 3/2, and f of 2. So go to your calculator. And we can do this really quickly in your calculator. And your y equals, put in the equation. So 2x squared plus 3 is my equation. I'm going to put in my y equals. So 2x squared plus 3. And then, since I'm a visual person, I like the graph. You can do the table if you're a person that likes tables better. But I like the graph, so I'm just going to graph it. Now, I need to know the function value at 1/2. So I'm going to hit trace 0.5. Enter. It gives me my function value of 3.5. So I'm going to put 3.5 there. Okay. Then I'm going to do 1. Enter. Function value at 1 is 5. So I got my answer. Then my next one is 3/2, so that's 1.5. Enter. That's equal to 7.5. And then function value at 2. Enter. That is 11. So back on my paper where I show my work, I don't even have to show this graph. You don't have to do this graph on your paper. But you can go back to your paper here. And then I just put in that information. So I would say my next line is 1/2 times 3.5 plus 5 plus 7.5 plus 11. So use your calculators as tools. And now I just need to figure that out. So I'm just going to add those together and multiply by 1/2. So 3.5 plus 5 plus 7.5 plus 11 times it by 1/2. 13.5. Done. That's all the work I need to see. Okay. You don't even have to show this, but I like to show this to figure out where my groupings are, but you don't have to do that. So everything over here is what I need to see. The delta x and doing the r. Any questions over that? We'll do one more. We'll do the midpoint. Midpoint's always fun. So we'll do the midpoint one. Okay, so our interval is the same. So we're doing the same interval. So my delta x is going to be 1/2. That's easy. Now, looking at my first interval, it goes from 0 to 1/2. What's our midpoint value? What is that? I need the function value at 1/4, or I can do 0.25. We'll probably have our calculator. I'll go to 0.25. Okay, what's the midpoint here between 1/2 and 1? Okay, 0.75. Midpoint here between 1 and 1.5. 1.25. And then the midpoint between 1.5 and 2. 1.75. Okay, then I'm going to go to my calculator again. I'm still on the graph, so it makes it easy. I'm still on trace. And I needed to figure out, what was the first one? 0.25. So 0.25 equals 3.125. So that's 1.25, what was that again? 0.25 is 3.125, 0.75, 4.125, 1.25, 6.125. See how fast this is with my calculator? 1.75, 9.125. Okay. And then I just add those together. Do not round yet until the end. And multiply by 1/2. and I get 11.25. I will give you a hint on this workout, this sheet. It says round to 2 decimal places. So if you round it here to 2 decimal places, your final answer will be off and you will not get points. It's not a drop down. You have to type it in. You got to type it in exact to get the points. But if it's something like this, if it's 13.5, I want you to just write 13.5. You don't have to write the 0. Don't write the 0 there. Okay? Because that's how I did your answers. And that's it. That's the last method on the Riemann sums. Questions over that? Okay, now I'll just finish up the worksheet.